Okay, so now we're in chapter 6, and we're talking about microservices, which is very similar to services. So, let's talk about services. Software services. A software service, because we talked before about SaaS, right? Software as a service. So what are microservices? So let's remind ourselves about the services. A software service is a software component that can be accessed from remote computers over the internet. Well, we've said that. Given an input, a service produces a corresponding output without side effects. This, in other words, it just gives you what you asked for. The service is accessed through its published interface, and all details of the service implementation are hidden. And that's what I call like an API, the published interface. It means that, like, if you want to know certain information, let's say you want to know the weather in Bermuda. So there's a weather service, and it tells you, I need to, and you'll read its API, you'll read its published interface, and it'll tell you, give me these 6 fields, and then I'll give you the data. So in other words, the fields might be the name, Bermuda, the date, whatever information you have to give it, and you'll send that on the internet, like as a, it could be HTTP request. You'll send it, and then you'll get back a response. Services do not maintain an internal state. We mentioned that, which means state again means remembering sequence. They don't remember sequence. They just, anytime you ask for the weather in Bermuda, I'll give you the weather in Bermuda. Yeah, I'm not going to give you, like, because you asked yesterday for the weather in Bermuda, and you asked, I'm going to assume anything about what, and you asked for it, for 12 o'clock midnight, then I'm not going to give you 12 o'clock midnight this time because that was the last request. I don't remember what your last request was. So services do not maintain internal state. State information is either stored in a database or is maintained by the service requester. And if you want to maintain state, that's your problem. When a certain, the requester has to maintain it. When a service request is made, right, if he does want to give state information, so he has to pass it. In other words, I'm requesting this, but I'm requesting in this certain circumstance, then he has to pass it as part of the request and update the state information. And the updated state information is returned as part of the service request. There is no local state. Services can be dynamically reallocated from one virtual server to another and replicated across several servers. In other words, the server doesn't maintain its own state. Modern web services. So after various experiments in the 1990s with service-oriented computing, the idea of big web services emerged in the early 2000s. These were based on XML-based protocols and standards such as SOAP for service interaction and WSDL for interface description. Most software services don't need the generality that is inherent in the design of web services. Consequently, modern service-oriented systems use simpler, lighter weight services interaction protocols that have lower overheads and consequently faster execution. In other words, the services have gotten smaller. The types of things you're requesting are like what I'm saying, whether, just as a particular single piece of information. Microservices are small-scale stateless services that have a single responsibility. They are combined together to create applications. They are completely independent with their own database and user interface management code. Software products that use microservices have microservices architecture. If you need to create a cloud-based software products that are adaptable, scalable, and resilient, then I recommend that you design them around microservices. So here's an example. System authentication. In order to have a system with authentication, I have to have various things like user registration, where users provide information about their identity, their security information, their mobile, cell phone. They register for, they join up to a website. Then another service that I might provide is authentication. For example, they give me their name and their password and I let them in. And then there may be two-factor authentication, where I send them a code to their mobile and they give me back that code. And these are all different features that are involved with the concept of authentication. User information management. Maybe they want to change their password or change their mobile phone number. These are all things that I'm going to have to provide if I'm going to give a complete system for user system authentication. And they may want to have a reset forgotten password. So all this is in a certain component called system authentication. Each of these features, there are 5 features here, could be implemented as separate services that uses a central shared database to hold authentication. In other words, I could have a service called reset password or a service called register user. However, these features are too large to be microservices. That would not be called a microservice. To identify the microservice that may be used in the authentication system, you need to break down the coarse-grained features into more detailed functions. So let's see how would we chop up this sort of larger service into smaller parts. So we talked about, the first one was user registration, then was authentication. So here we're going to see user registration. User registration actually is a set of small activities. For example, first of all, I need to create an ID, the username, and then I need to create a password. And those are different activities. Then I need to set up password recovery information, set up two-factor authentication, as get this mobile phone number, and confirm registration. Needs to say, yes, I want to register. Each of these is a feature of user registration. Authentication using user ID and password. So I need to get the login, get the password, check the credentials, and then confirm the authentication. These are the steps that are all involved in a person logging in. Right. So if I broke it into microsystems, I might have microservices. I might have a user ID management. It's just dealing with his user ID. You know, letting him choose his user ID and telling him this is available, this is not available. And for that, I need to go to a database about user IDs. Then I could also have password management, where I let him set his password and I store the password and I encrypt the password. User information management. I have other information like his mobile phone number. And all of these are different services. They're not in this large grouping. It's a different grouping. And the point is that this is self-contained. And all I'm doing is creating a new user ID. And he doesn't need to know anything about passwords in order to do that. It's its own little system. So characteristics of microservices. Microservices do not have external dependencies. They manage their own data and implement their own user interface. In other words, each one is independent. They're lightweight. They use lightweight protocols. In other words, you don't have to give a lot of information to get back the information you want. So the overheads are low. Implementation independent. This is actually the key point. I think microservices may be implemented using different programming language and may use different technologies. In other words, I could do this in C++ and this in PHP and this in Python. And the databases could be all on different machines and different types of databases. And how will they all integrate? They'll all integrate because it's all using HTTP communication. I don't know if you guys understand this. I should show you a picture of HTTP communication. Yeah. Here, we're talking about JSON. But let's see. Yeah, here. Okay. Yeah, this is where we're getting to. You see, for example, we were already at slide 41. Maybe we'll go back. This is where we're going to. If HTTP request and response message organization. So I make a request, and I make a request. I HTTP verb like put or get, URI, the universal resource identifier, in other words, the URL, and the HTTP version that I'm using. I send that information along with the request header and the actual body. And then I get a response that's also in the same format, HTTP version, the response code, the response header, and the actual body. Basically, the body is the information I'm interested in. This is just sort of routing information. This is routing information, and the length of the request is in the header. But the actual body is here. And here's the actual body of the response. Now, how does that body look? That body looks like this. For example, this would be a JSON request with parentheses, braces, and then field name colon value. Field name date colon value. Time is also the name colon value. And I give all the names of the fields and their values. Description. Broken down bus on North Carriageway, 1 lane closed. Expect delays of up to 30 minutes. So this is like for a traffic for a, traffic report information, maybe for like Waze. Somebody, maybe that's information that gets sent back to the server. That would be a request. That would be the body of my request. Now you see what my point was about writing it in different languages. It doesn't matter how I create this is actually a string, right? It's just a long string of characters. I could create that string using cout in C++ or using print in PHP or Python. In other words, it doesn't matter what language I'm writing, as long as I create this string and send it via an HTTP message, which I'll have to have libraries for, in my programming language. So it doesn't matter what language I write the service in, as long as I know how to handle a string like this and give a response. Here, by the way, is an XML request. As I can choose. In other words, when I write a service, I'll say I expect an XML request or I expect a JSON request. Theoretically, I could write it for both. I could support both, but usually they're alternatives. So an alternative is to use XML, which instead of being, like we saw here, field value, it's field inside of the tag, inside of these less than greater than signs, and then close tag. So the ID field, and here it's value. The date field, and here it's value. So people don't like the XML because it's like you have to close every field and it's longer to look at. It's more like HTTP, like it's more like XML. It's more like not XML. It's more like HTML, and it was designed to work compatibly with HTML. But nowadays, people prefer the JSON because it's like more short. You don't have to. You just write a colon between the fields, but you do have to put parentheses. Whatever. It's more. People appreciate that. But the point is that when I do a service request, I give them something like this, and I get back a JSON with the answer, with the data that I'm interested in. If this is just a post, maybe I just want to have a date. Maybe my response would just be received. It'd be like, received colon yes, something like that. And then I, in my software, check for that response. In other words, if I don't get that, then I send it again, for example. So this means that these services are language independent, because as long as I'm providing, they have to be in English. They have to be according to the rules that the service told me. That's what I said. It has to publish its API or its way of working. That's what we saw. Where is it? I'm really just explaining. Where is it? I'm really explaining their. Wait. I'm explaining why they're independent of a language. I thought we mentioned something about that. Let's see it now. Here. The service is accessed through its published interface. That's what I was saying. Its published interface is that XML format, how the XML should look, and what kind of response I'm going to give you. I publish that. And then it doesn't matter how you create your service request. As long as you follow the format, you'll get your response. So therefore, they're language independent. So anyway, we're talking about now breaking this down, this example of authentication, microservice management, how you break it down. So we broke this down into some smaller services. Oh, I was saying here. Microservices may be implemented using different programming languages. That's what I was explaining. And may use different technologies. Because I don't care. I don't know how the databases are being stored. One service may store it on one kind of database, on the other on another database. Independently deployable. Each microservice runs in its own process, is independently deployable using automated systems. Right. There's no, they're completely separated. Business oriented. Microservices should implement business capabilities and needs rather than simply provide a technical service. Right. Somebody has to be willing to pay for whatever you're giving. Okay. Microservice communication. They communicate by exchanging messages. The reason why I gave you that, I jumped to the end, is because now this is going to be much more straightforward. Obviously, they communicate by exchanging messages, as we just saw. The messages of the XML or the JSON. A message that is sent between services includes some administrative information, like the service, like the type of the type of HTTP I'm using, if it's HTTP or HTTPS, or is it Internet version 6 or version 4, a service request and the data required, a service request, like what request am I actually making, and the data required to deliver the requested service. But we didn't see that in the JSON, what the request was. We just saw the data. But there could also be a field what the request code is. Could be code, 1, and 1 means this kind of thing. 2 is this. Service return response to a service request, an authentication service may send a message to a login service that includes the name input by the user. Right. It may send you back. If I put in a login name, you may send it back to me. The response may be a token associated with a valid username. It could also be a token, or might be an error saying that there's no registered user. A well-designed microservice should have high cohesion and low coupling. These are famous terms that you should have seen in your introductory course. Cohesion and coupling. Cohesion is, we want to have high cohesion, which is a measure of the number of relationships that parts of a component have with each other. High cohesion means that all the parts that are needed to deliver the component's functionality are included in the component. In other words, this is a key idea here, this cohesion and coupling. Cohesion means that everything that this service needs to get its job done, it has. It doesn't need to go and make other requests to other services to get more information. most of the information it has. It maybe makes a few small requests to other services, but it has that's why we don't talk about 100% cohesion. We mean high level of cohesion. It can do its job without having to rely on other services too much. Coupling is a measure of the number of relationships that one component has with other components in the system. Low coupling means that the components do not have many relationships with other components. It's kind of the same thing. Now, there's coupling means, am I coupled together with another? That's kind of what I described before. Am I coupled together with another service? And you need both of us to get your result. As I need to use this other service. And cohesion means, am I doing everything that I need to do to give you what you need to respond? Or another way of thinking about, actually a better definition of cohesion, what's written here is not really that great. Well, it does sort of say what I want to say. That means that all the parts that are needed to deliver the component functionality are included. In other words, but I would say to the exclusion of other parts. There are no parts in it that are not necessary. Everything that I need is there, and nothing that I don't need is there. It does like here it says, each microservice should have a single responsibility. It should do one thing only, and it should do it well. Now, it should only do one thing. It shouldn't try to do other things. And it shouldn't request things from other people. In other words, it shouldn't do multiple things, and it shouldn't require, on the other hand, it shouldn't require from other services needs. However, one thing only is difficult to define in a way that is applicable to all services. Responsibility does not always mean a single functional activity. In other words, these two ideas are hard to define. It's hard to know if that's why if you really obviously you might have some service that I use, and I might do something extra, like I might record, like if, for example, if he asks me for a username and I tell him this is an available username, so that's all I should be doing, right? But I might also be recording that there was a request for this username, because maybe I'm keeping statistics on what are popular requests. So technically that might be violating the idea of cohesion, because I'm doing something extra. But it's a small extra thing, so it's not so it's okay. In other words, cohesion should be high, but not infinitely high. And coupling also, maybe but in other words, if a person gets obsessive about cohesion, he may break up all of his things into very small parts, and then I may have, to get anything done, I may have to call 25 services, and it may get crazy. So everything has to be done in a balanced way. So we're going back to our example. We're redefining the system, basically. You know, we're not breaking up. If we talked about this system, authentication, we talked about, this is here. We talked about resetting a forgotten password, for example. We talked about these 5 different things that I want to do, or user information management, changing a password, or a mobile phone number. These were the original way we tried to divide up the system, and now we're going to try to divide it up in a different way. Like this, we're going to have user functions: create password first time, change password, check password, check for like authentication, check if that's the right password, recover password. So these are all things that are discrete things. Checking a password, supporting functions. In other words, in order to get check password done, I need to check its validity, which might mean, is it a valid password at all? If maybe all of our passwords have to have 1 capital and 1 lowercase and 1 number, at least, and they have to be 8 digits long. So I maybe check its validity even before I check if it exists in our database. If the password can't be a password, then I tell them it's not your password. Delete password. Delete password may be part of change password, right? First, when I want to change password, I delete the old one and create the new one. In other words, change password may actually make a call to delete password and then make a call to create password up above. Backup password in the database. So this is when I create a password, I also back it up. Okay, so these are supporting functions. So how microservice X, how should it look? Service function, message management, failure management. These are all things that every service needs to have. It needs to have a way of handling failure, a way of handling passing messages, a way of maintaining data consistency, and it must have some kind of user interface, a way of using it. A microservice architecture is an architectural style, a tried and tested way of implementing a logical software architecture. This architectural style addresses two problems with monolithic applications. So a monolithic application is just writing, like what you did in your first year, writing a program, just one program. The problem with monolithic programs is that the whole system has to be rebuilt, retested, and redeployed when any change is made, right? If you change something in your system, then you have to rebuild the whole thing, and then if it works, then you got to reinstall it everywhere where it was, if you want to make one change. This can be slow. A slow process as changes to one part of the system can adversely affect other components. I have to debug. I have to make sure everything is still working. I have to run it through all the tests. That's the problem with monolithic. But if I have services, then I have a specific service that it just gets a request and gives back a certain piece of data. If I want to change one of those services and how it's internally working, as long as its external interface doesn't change, then I don't have to change anything else in the system. As the demands on the system increase, the whole system has to be scaled. Yeah, if I all of a sudden, yeah, if the demand, I have to put a bigger and more powerful computer because I have it, I don't have my services distributed over many servers. If the demand is localized to a small number of system components that implement the most popular system functions, it would be nice if I could just increase the number of, in other words, let's say that I get lots and lots of requests for password changes, but I don't get lots of requests for new accounts. Let's say Google, everybody who wants a Gmail Google account already has one by now. So most of their requests are for change of password and not for creating new accounts. So it could be that the number of servers they have for that part, for the changing password, could be a larger number of servers than the number of servers they have for creating new accounts, which is very rare, perhaps. So if it would be a monolithic software, then I would have to just increase the number of servers across the board because I just have every server does everything. So it's more efficient to have these microservices. I'm able to expand the parts of the system that have the most stress on them. Benefits of microservice architecture. Microservices are self-contained and run in separate processes. So one process getting stuck won't affect another process. In cloud-based system, each microservice may be deployed in its own container. This means a microservice can be stopped and restarted without affecting other parts of the system because they're each in their own container. I can restart them, and I don't have to restart the whole system. I just can reset the service. And I'll build my systems. I'll build all my requests with timeouts. So when I make a request to get information, if I don't get it in a certain amount of time, I'll re-request. So that means that I have robustness. If I restart a server, so it was down when I made the request, but when it comes up, I'll make the request again because I had a timeout. So that means I can take any part of the system and turn it off and turn it on again. and the system will continue running. And I don't have to restart everything at once. If the demand on a service increases, service replicas can quickly be created. In other words, if all of a sudden people are changing their passwords a lot because there was a bug or a hack that was announced, so now I can increase the number of servers that deal with those requests and not have to increase all my servers. These do not require a more powerful server, so I can do scaling out instead of scaling up. I'll just add more servers to the part of the system that is being stressed at the moment. This is a key idea of the microservices. Here's another example: a photo printing system for mobile devices. In other words, I have, let's say, an app that you upload your picture to it, and then it prints the picture and mails it to you physically. So imagine that you are developing a photo printing service for mobile devices. Users can upload photos to your server from their phone or specify photos from their Instagram account that they would like to be printed. Prints can be made at different sizes and different medium. Users can choose print size, print medium. For example, they may decide to print on a mug or a t-shirt or on paper. The prints or other media are prepared and then posted and is mailed to your actual physical home. They pay for the prints using a payment service like Android or Apple Pay or PayPal, or by registering a credit card with the printing service. So what are the microservices that we would have for such a system? So first of all, here's the mobile app on your phone, which you've downloaded. Now the mobile app is going to communicate with an API gateway. In other words, API, again, when you see the word API, think of XML or JSON. In other words, the mobile app is going to send a JSON to this gateway with a particular request saying, I want to register. And the first field, let's say, in the JSON would be what type of request it is. Is it a registration, authentication, upload, payment, printing, or dispatch? And I will make the registration information and get back the data, and he'll send it to my app. You register. I want to upload a picture, he'll do upload. Now, in my upload request, what data am I going to have to send? I'm going to have to send again my username, because how do we know that we don't know that this is the same guy? We have no way of knowing it's the same guy. We're just sitting here waiting for upload requests from all the world. So it'll have to be that the username comes back. You say, well, wait a second. What if I write a malicious app and I know the API gateway and I write my own app that sends somebody else's user ID, username, and uploads to his account or something like that, or uploads from his account to his account, whatever, or his payment. So the answer is that when I log in, when I authenticate here, there will be some kind of token that gets sent to my app. And that'll be some very long number. And every time I make a request, I'm going to send back that token. And that token, I'll have to send back the token and the username. And therefore, I can't do anything to any other user because I don't have his token. But therefore, it's stateless because I don't have to remember that I'm already logged in. In other words, I'm not maintaining information that he authenticated. You see, that's the key idea of the statelessness. I'm not maintaining, okay, this guy is logged in. Every time I logged in just means that I got a token. And now I send back this long number, this token, every time. Now, you as a user don't see that. You just click on a button. But the app, that's what the app is doing. And therefore, all of these services are stateless. And they can't be hacked. I mean, you could try a million times this long number, but it'll probably, after a certain number of attempts, it'll probably stop you. Microservices architecture, key design questions. So these are the questions you need to ask when you're designing your system. What are the microservices that make up the system? Now, you need to be able to divide your system into microservices. If you can't do that, then it's going to have to be monolithic. What should the microservices communicate? How should they communicate with each other? Well, like through the app or through a web browser. How should your service failure be detected or reported and managed? If a certain service is not working, we may have to restart it. How are we going to figure that out? How are we going to find that out, that it stopped working? We have to have some kind of monitor. Maybe the apps will automatically send to some other monitor. How should the microservices in the system be coordinated? Right. Is there going to, is it going to be through the mobile? The way I described it is that the mobile app would coordinate. The mobile app would know what you're requesting and make their correct service requests. How should data be distributed and shared? Should they have a shared database or not? They could theoretically have a shared database. Okay. Decomposition guidelines. So how are you going to divide up your functionality? Balance fine-grained functionality and system performance. So you need to balance between having things fine-grained and not making the system too slow because you have too many parts. Single function services means that changes, this goes back to our idea of cohesion and coupling. That you want the functions to be it's sort of you want the functions to be relatively cohesive. Single function services means that changes are limited to few services but require service communication to implement user functionality. This slows down a system because of the need for each service to bundle and unbundle messages sent from other services. In other words, the smaller fine grain your functions are, the more requests you'll have to have. And therefore, the more unbundling and bundling of messages, the more interpreting of messages, slowing down your system. Also, fundamentally, communication is slow because it's going over wires between remote places. So follow the common closure principle. Elements of a system that are likely to be, here's a very good, important rule. Elements of a system that are likely to be changed at the same time should be located within the same service. In other words, if you think that you're going to change your, let's say the rules of your passwords, instead of 8 letters long, now they have to be 14 letters long. So when I change that, what other things might I change? I might also change the rules. I might change the way I authenticate. I might change other things. So they should be all in the same service. So that would be a reason to make a service bigger and less micro. In other words, make it more cohesive. Cohesiveness tangentially basically makes the service larger, whereas a fear of coupling may cohesion makes it larger, right? And coupling also. Most new and changed requirements should therefore only affect a single service. Let's try to have everything that would change together in one place, in one function, in one service. Associate services with business capabilities. A business capability is a discrete area of business functionality that is the responsibility of an individual or a group. You should identify the services that are required to support each business capability. Well, that's kind of the way they divide things up over here. In other words, this is a business capability, upload. I have a feature in my software that they can upload pictures. So that's a service. Don't try to divide that up into parts. It's a business service, and it's from the perspective of something a client may want. Design services so that they only have access to the data that they need. This is a very important principle also, which is saying, like, deny yourself access to data that you don't need. In other words, make rules about access. If there's, in other words, I'd rather not allow a certain service to have access to data that he doesn't need. If he turns out he does need more data, then I can give him that access. But while the program is, at the current moment, the program should be designed such that he can't access data that he doesn't need, because that invites hacking. if there is an overlap between the data used by different services, you need a mechanism to propagate changes, right? If two services share the same data, then there needs to be some kind of, like we talked about, ACID transactions, and propagating the changes so that they all have the same data. You should read about ACID transactions after class. Services communicate by exchanging messages that include information about the originator of the message, as well as the data that is the input to or output from the request. So that's the XML we were talking about. You'll have, that's how they communicate, by exchanging messages. That's the data. When you are designing a microservice architecture, you have to establish a standard for communications that all microservices should follow. In other words, let's say the first of all, the standard could be use JSON or use XML, or that the first field should be the type of request it is. When you are designated a microservice architecture, you have to establish, some of the key decisions you have to make are, should service interactions be synchronous or asynchronous? So that means, should they come with a timestamp or not? When I request, should I continue? There's different definitions of asynchronous and synchronous. I think what they mean actually here is, when I make the request, do I wait for the response to come before going on? Or do I continue going on and the response will come whenever it comes? That would be asynchronous if I don't wait. But if I wait for the response before proceeding, then that would be synchronous. Should services communicate directly or via message brokered middleway? Does one service talk to another service, or is there a middleman? What protocol should be used for messages exchanged between services? What protocol? JSON, XML, HTTP. What message? I mean, HTTP is probably going to be the message. So here is a definition of synchronous and asynchronous, which I already explained. Basically, service this is synchronous, which means I wait for I'm processing, then I make a call to service B, please give me the response. B figures it out, tells me back, and once he told me, then I only continue. As opposed to service A is processing, he makes a request to B and doesn't wait. He immediately goes on to the next process. And whenever that response comes back, he puts it in some kind of queue. And at some point, A will check the queue. But that didn't stop it from continuing to process. That's asynchronous. In synchronous interaction, service A issues a request to service B then service A then suspends processing while waiting for B. It waits until B has returned the required information before continuing. In an asynchronous system, this is just what I said. Service A issues the request, that is the request that is queued for processing by service B, because B may have multiple requests. A then continues processing without waiting for B to finish the computation. It just goes on. Sometime later, B completes his request and sends it to a queue for A. And A will check his queue at some point. Service A, therefore, has to check his queue periodically to see if the result is available. So here is direct and indirect communication, which means service A just talk to each other, and here's a message broker. They talk via a broker. All right. Direct and indirect service communication. Direct service communication requires interaction. It requires the interacting service to know about each other's existence and their addresses. In other words, I need to know your IP. Each service has to sort of know where the other one is. It's to know his IP, his name. The service interacts by sending direct requests to these addresses. Indirect communication involves naming the service that is required and sending that request to a message broker. In other words, I have to name where I want my message to be sent, so the broker knows where to send it. In the first one, I don't have to name it because I'm sending it directly to that service. The message broker is then responsible for finding the service that can fulfill the request. I would suggest that the message broker is the way to go, because then I can swap out, and only he has to know about the location of the servers. Here, though, I do save in my HTML. I don't have to say what the request is. It's obvious what the request is. The request is the only service that service A provides, which is service A. And he only does one thing. So if I'm requesting from him, I'm obviously asking for that thing. Here, I have to say what I'm asking for. But it gives me the flexibility of swapping out A with a new version of A, or a new IP, or a new location. All right, we'll stop here and we'll continue with slide 23 next time. Any questions before